So we will go through this very quickly. So A and B are complex ions, and the metals ion and the ligands coordinated to it. Okay, so all these A and B. So this question is very similar to the previous paper as well, like 18 and 7. So you see now the trend is little bit of changing. So these are complex ions with octahedral geometry. Okay, so these are octahedral. So basically there should be is octahedral. So 6 ligands attached to the metal, right? And they have the same atomic composition, Mn, C5, H3, and N6. Each complex, the two types of ligands are coordinated to the metal ion. So this is an additional factor that we need to remember. So the formula is this, it is not going to change. And only two types of ligands are coordinated. That is one. When an aqueous solution of containing A is treated with potassium salt, so there's a potassium salt, the coordination compound C is formed. Okay. So when you add potassium, which is a salt, a coordination compound C. So this is a different compound. So think about this. You have A, and you add potassium salt, which is K plus here. So K plus should coordinate with this compound A, which is an aqueous solution. So this gives you the idea. A might have some sort of charge in its structure, right? Otherwise, how this potassium is going to coordinate and form this coordination compound C, which is a different compound, right? C gives 4 ions. This is an important factor. So C gives 4 ions, right? C gives 4 ions. So it could be like 3 potassium ions plus negatively charged 3 minus compound of A, or either it could be 2 negatively charged 2 minus charge of the A or 2 potassiums. So we don't know. So we have to check whether it gives 4 ions or not. So this is one of the things that we need to find. When an aqueous solution of B is treated with potassium salt, the coordination compound D is formed. So D is also formed. D gives 3 ions. So this is another factor that is very important here. Both C and D still have the octahedral geometry, which gives you the idea the ligands in the inner sphere is not changed. The number of ligands. In fact, here the ligands is still 6. So don't forget about that. So the ligand number is not changed and everything is not changed. So we have to make sure what is actually happening here. The oxidation states of manganese in A and B do not change on treatment with the potassium salt. So it is very easy, right? So we have to go through this again. So I will stop sharing and quickly use the board to explain the situation here. Okay, that is part A. Then we have the final part B. So I will stop sharing. Right. So we will discuss this question very quickly without taking much time. Right, a common formula is given, right? So the common formula is Mn C5 H3N6, right? So this is C5. Now think about a situation where, okay, so now think about this A and B should be octahedral. That is one point. Octahedral. Second point is only 2 types of ligands should be there in A and B, right? Now this is the metal that is that we think. So manganese is normally present as Mn2+. So manganese normally does not have Mn3+, 4+. In fact, manganese has the widest range, like up to Mn+7. But in coordination compounds, normally manganese is present as Mn2+ in most cases. So keep that point in the mind also. In mind. Now we will consider about the ligands. So here we have carbon, hydrogen, and nitrogen. Carbon, hydrogen, and nitrogen. Now think what type of ligands that we generally use in our studies using these elements. Okay, so one that comes to my mind directly is this could be ammonia, 1 nitrogen and 3 hydrogen that can form ammonia. And the other thing is maybe carbon and nitrogen forming Cn-. This also can be possible. And what are the other ligands that can form this? These are the two possible options that I see here. Or maybe NH2- in some case with a negatively charged species. So it could be NH2 with a negative charge. So these three. In fact, these three compounds can be obtained as ligands, right? But in the coordination compound here, don't forget, there can be only 2 types of ligands. So it should be 2 of these 3. We don't know, right? Now we need to go to the composition. So composition, think about the composition. Here nitrogen, there are 6. Hydrogen, there are 3. And carbon, there are 5. So if I take one ammonia out of this, like this, so what is the remaining thing? So 1 nitrogen is gone here, so N5. Hydrogen is completely gone, so only carbon remains. So I have 5 carbon and 5 nitrogen, which gives me the idea, so it can be Cn. So basically this can be 5 Cn and 1 ammonia, 5 Cn and 1 ammonia, which gives me 6 ligands for my coordination. Because the first point is my metal is octahedral in geometry. Okay, so that is one point that you need to understand here. But if you take NH2, here there will be 1 hydrogen additionally that is going to remain. And when you try to make 5 Cn, this hydrogen is remaining. So you cannot go for octahedral geometry. You have to go something else. This hydrogen could be H-. So you will have 7 ligands. So there is a problem. Like 1 NH2, 5 Cn, and 1 H-. So it is 7. So it is very difficult to compare. So that is why this H- can be, for an example, if that is a ligand, this could be here in NH2, then this can be as an ammonia ligand. So we can come to a conclusion, our ligands here could be Cn- and NH3. Okay, so that is the first point. Second, come to the description again. I will share the screen again. So A reacting with the potassium salt. So here I will just write down this. A with potassium salt and B with potassium salt gives a coordination compound, and they are still in octahedral geometry, which gives these ligands are not changed still. But when C dissolves, C gives 4 ions. So C gives you 4 ions and D gives you 3 ions. That's the idea. Now think about this a bit. I will stop sharing again. Okay. So C gives 4 ions, D gives 3 ions, right? So according to this piece of information, where my ligands are Cn minus and ammonia, my compound could be Mn Cn 5 NH3. Okay, that is when we have these 6 ligands that is coordinated to my metal, which is manganese, and this should have some sort of a negative charge. I'm not telling what is the negative charge now here. I will tell that in a moment. So here this should have a negative charge so that potassium here from the salt, potassium here from the salt can combine with this negatively charged species and form the coordination compound C and D. The easiest way to find how many potassiums are going to bind is from the fact they have given the amount of ions that are formed, right? So how to determine here? So one of the ions should be this one. So this is my 1 ion. So from 3, 1 ion should be my this coordinative negatively charged species, and the other 2 surely from potassium plus. That is how this will give 3 ions to the medium. And here for in this one, 1 should be from my negatively charged species, and the other 3 should be from the potassium ions. That gives you 4 ions in the medium, which finally gives me the idea. The compound which gives 3 ions should have something like K2 Mn Cn5 NH3, and the compound that gives you 4 ions should have K3 Mn Cn5 NH3. So when you dissolve this one, there will be 1 ion from this because that is a coordinated compound, and 2 K plus, which makes 3. And here from this 1, 3K plus, total is 4. Okay. So what is the final step? The final step is checking the charge of manganese. In fact, the oxidation state. Because if this is K2 plus, here this coordinated compound is 2 minus. If this is K3 plus, here this is 3 minus. So which gives you the idea, C that is coming from A, which gives you 4 ions, should have a negative charge which is -3. So this is basically A, and this is basically B, and the whole compound from A and potassium is C, and the whole compound from B and to potassium is D. Okay, now this is very straightforward. So as the final step, so what is the oxidation state of manganese? So think about this. If this is 3 minus, there is 5 Cn ligands, so this is -5. So -5, ammonia is normally not charged here. So -5 to make -3, this manganese should be +2. And here this is -5 to make -2, this manganese should be +3. Okay, so this is how you can go through this description and find the 2 coordination compounds. Okay, now this question is very easy when you compare to the 2017 question that we discussed earlier. Okay, because there was a big description to find these 2 positive ions, if you remember about. They add with some AgNO3 to precipitate out as AgCl. So it's many things. Okay. When you compare this with that question, this question is a little bit easy. So this is the way that you can approach this question. So anyway, when you find this type of question, first try to identify the ligand, then try to identify how much ions they give to the solution. Based on that, try to identify the oxidation state and the charge of the coordination compound. And So that's the easiest way to perform the operation for this type of a question. Okay, so I will again share the screen here. So identify the ligands coordinated to manganese A in A and B. So basically it should be Cn minus and NH3, right? So I will use a different color. So give the structure of A, B, C, D. So A and B should be the negatively charged species, and C and D with potassium that is attached to the as an outer sphere counter ion. Okay. Write the electronic configuration of the manganese ions in A and B. So in A, manganese was in +2 oxidation state. So here it is Mn2 plus, and here it is Mn3 plus. So don't forget to write down the oxidation state, and then write down the electronic configuration. Write the IUPAC names of C and D. So C, you have 3 potassiums. So you have to write first potassium, keep a small space. So because C is, so I will stop sharing and show that in the board. So C is this compound that is going to form from A. So potassium, keep a small space, then the negatively charged anion. So it should be amine here, and pentacyanide. You cannot use now cyano because now the rules are different. So cyanide, but you cannot still keep this as manganese because the charge is negative. So you have to put the ate suffix. So this could be manganate. And you have to mention the oxidation state in the parentheses as 2. And for this one, potassium, the same amine, cyanide, this manganate, and the oxidation state should be put as in the parentheses as 3. Okay. So those are very, very basic things that you should know, and you should be able to understand. Okay. So I will share the screen again. So this is the first part, right? 1, 2, 3, 4. So that is done. And we have to move towards the last part now, which is part of the electrochemistry, right? So we know what is actually coming from question number 10, last part every time when we discuss, right? So we will go through it very quickly. Right, so write the reduction half reaction corresponding to the electrode which is given here, right? So Ag solid, AgCl solid, Cl minus. So they are asking about the reduction half reaction. So reduction basically happen here from Ag plus, that gives you Ag, that is the reduction. But here we don't see Ag plus, so this should be AgCl here. So basically it is AgCl solid. So please show the physical state plus electron that gives you Ag solid plus Cl minus Aq, right? So don't forget to mention the physical state. State whether the electrode potential of Ag, this particular electrode that is given, depends on the Ag plus concentration in the solution. So when you consider about this reduction reaction, this would be the opposite direction would be its oxidation reaction. So here you see here, no Ag plus is involved in the reduction process. Okay, because this is Ag solid, Cl minus equals AgCl solid. So no Ag plus involvement. So this will not affect the potential, like for the electrode potential. So no Ag plus involvement. So it will not affect the potential. Okay, so these two. Then the second one, consider the following reaction. Fe with 2H plus and oxygen gives you Fe2 plus and H2O. So you see here Fe is oxidized while H plus is reduced. Okay. Write the oxidation and reduction half reactions. So oxidation half reaction is Fe solid gives you Fe2 plus. So this should give Fe2 plus 2 electrons. So show the physical states. That is very important here. And the rest reaction is half O2 gas, we'd say, plus 2H plus. That is going to give H2O liquid, right? Okay, so here to balance the charge, you need to add 2 electrons because this is the reduction reaction. So everything is okay here, oxidation and reduction, because the oxidation is happening here, reduction is happening here. Okay. Given that the above reaction is a cell reaction of electrochemical cell, okay, so now they are going to prepare electrochemical cell using this, let's say this is the oxidation reaction, and this was our reduction reaction. So they are going to prepare electrochemical cell, which is very nice. And they try to say determine the electromotive cell. So you know this. So E cell is going to be E cathode minus E anode. So write down that equation. Or E cell is going to equal E cathode. So what is the cathode here? Positive. This is cathode. So it will be E H plus, and the entire thing here can write down minus E anode, which is E Fe2 plus here. You have to put the physical state as aqueous, and Fe solid here, and then you can show the calculation. So it is 1.23 volts minus 0.44 volts. So this gives you the value 1.67 volts. It's nice. Okay, so this is also done. And the last part is again about some small calculation. A constant current of 100 milliampere was passed through this solution, which is given as calcium 2 plus calcium bromide, and the temperature was remain constant. And so you see here they have used inert electrodes, platinum. So they try to now do the electrolysis using the current flow. Okay, write the oxidation and reduction reaction that takes place at the electron. So oxidation, so it is the anions that is going to perform the oxidation, right? So what are the anions? There is Br minus, but don't forget this is aqueous. So there will be some OH minus, and there will be some H plus as well. So my oxidation reaction from OH minus and Br minus, it is always Br minus, right? So this is going to oxidize to Br2. You can either write gas, or even this is since this is in a liquid, you can write Br2 liquid. So 2 Br minus, Br2 liquid, 2 electrons. And the reduction reaction. So the reduction reaction is basically you have H plus and calcium 2 plus. So calcium 2 plus, they don't like to get reduced. So you can write down this as H plus, okay? So basically H plus with 2 H plus, in fact, 2 electrons will give you H2 gas, right? But normally we don't write like this. We always try to write whenever you have a reaction of H plus or OH minus from water, we always try to write down using its reaction with water, because it will be easy for you to understand the actual process. So normally we write this as the reduction process as 2H2O plus 2 electrons. So we add like 2 OH minus to this one, then it will give you 2 water, 2 electron. So there will be this hydrogen that is formed. Additionally, since you had 2 OH minus, so there will be 2 OH minus here as well. Okay. So don't forget these things. These are very important. So here you can mention this as gas. This is aqueous. So water is liquid here. So this is the oxidation and reduction reaction. Okay. And the last part is calculate the time taken for the commencement of the precipitation of the calcium hydroxide. So this becomes very simple here. In fact, they have given the solubility product of calcium hydroxide and neglect the ionization of water. Assume that the volume of the aqueous phase remain constant. So I will use the board very quickly to explain the situation. Okay. I will stop sharing. And yeah, so the idea is very simple. I will quickly tell what is actually happening here. So we had this platinum neutral inert electrodes. So we have this calcium 2+ and Br- solution. And in fact, you know the oxidation reaction. So it will be Br-2, Br to liquid, put the 2Br, 2 electrons. And then the reduction was 2H2O with 2 electrons, giving H2 gas plus 2OH-. So this was our reduction reaction, right? Now they are asking what time that you need to run in order to precipitate calcium hydroxide. Because from the reduction reaction, you see here, some amount of OH- is formed. So this OH- combined with this calcium 2+ to form calcium hydroxide, right? So you have to remember this precipitation happens when calcium 2+ concentration times OH- concentration exceeds its ionic product. So you can write down first point like for precipitation of calcium hydroxide, right? So precipitation of calcium hydroxide, the minimum OH- concentration needed. Okay, so it should be very, very equal to the Ksp value, right? So you know the Ksp value. The Ksp value is given. For an example, here in this question, the Ksp is given. It is 1 into 10 to the power -5. So you can write 1 into 10 to the power -5, which is the Ksp value. Put the units here. It will be equal to calcium 2+ aqueous concentration times OH- aqueous concentration to the power 2. And calcium 2+ concentration they have given as 0.1 nem solution, because this is a 0.1 nem solution. From that you can calculate here. So this will be 10 to the power -1, which will be cancelling out. So OH- aqueous concentration is 10 to the power -2 mol dm-3, because you will get here 10 to the power -4, and when you take the root, it will be 10 to the power -2, right? Now come here. So you found the minimum concentration in order to precipitate calcium hydroxide. That is 10 to the power -2 mol dm-3. Then you can take, to give away this amount of concentration of OH-, what is the amount of electron moles that is needed here? So you see the stoichiometry is 2:2. So the same amount of electron mole is necessary here, 10 to the power -2 moles, dm-3 for an example, if it is a concentration. But you know the volume is given 100 cubic centimeters, so you can multiply this by 100 into 10 to the power -3. So basically this will give 10 to the power -3 moles. So if you know the number of moles of electron, so you can multiply this by 96,500 coulomb per mole to calculate the charge needed. So the charge needed to achieve this amount of concentration is equal to the amount of electron mole that you are calculating here. For an example, 10 to the power -3 here. And then you need to multiply this by coulomb per mole. So here this will be in mole, So mole to per mole can cancel. So you will have a clear, nice 10 to the power minus 3 mole for an example here. So you will have 96.5 mole Coulomb. Then they have given the time, in fact, the current. So we need, from our physics, we know Q is equal to IT. So the time is equal to Q, the amount of charge over current. So the amount of current is what we calculated here. And the ampere value is given, I think it's 100 milliampere, so 0.1 ampere. So it is, where is it? I will check again now. So where is it? Yeah, so it is 100 milliampere, which is 0.1 ampere. So what you can do is you can do the calculation for 0.1. So it will be 965 seconds, right? Because here we find this as 96.5. Then you divide it by 0.1, so 965 seconds. Or you can divide this 965 by 60 seconds to give you give the answer for an example here. So 965 seconds, or you divide it by 60 seconds to give it that in minutes. So it will be very close to 16 minutes. Okay. So try to understand the process. To precipitate calcium hydroxide, you need at least the Ksp value of calcium hydroxide at 25 degrees Celsius. So you know the calcium 2 plus concentration. So we found how much OH minus concentration is needed. Then you can multiply this by the volume of the solution to get the OH minus number of moles, which is this 10 to the power minus 2 mole, right? In fact, 10 to the power minus 3 moles, because 10 to the power minus 2 is the concentration. So you multiply by 100 into 10 to the power minus 3, which is the volume. Then you get 10 to the power minus 3 moles, which is indicated here. So these two are same. And the same amount of electron mole is needed because the stoichiometry is 2:2. So same electron mole. So if you know the electron moles, you can multiply it by the Faraday's constant, which is charge per mole. So charge per mole multiplied by the mole factor, you get the amount of charge that is necessary. That is 96.5 Coulomb. When you find the number of charges, then you need to just divide it by the current, that is 0.1 ampere, then you get the time. So that is the basic and simplest explanation that I can give you for this particular calculation. Okay. So yeah, so that summarizes our discussion of this last part of this question number 8, 9, and 10. I have to break this into two because we had a small network problem in the middle. So I think it's done. So yeah. So I will stop sharing and I will stop recording, and we will see you next time. Okay.